right, everybody, welcome. This is Energy Week, and we are so excited because we have just started this is going to be the inaugural lecture of the Vagelos Institute for Energy Science and Technology. So we're going to do the yearly lecture at Energy Week, and we're so excited that Gillian Dempsey is here to be our first lecturer. So the idea behind this lecture is really to bring leading researchers from around the world here to Penn to talk to us about their approaches to solving what is the most massive problem that faces us as a society. Really, it's how we're going to transition our energy landscape to something that's sustainable. So we're really excited that Gillian is here. Gillian is an associate professor at the University of North Carolina, Chapel Hill, and she's currently the Bowman and Gordon Gray Distinguished Term Professor. She is also currently the Deputy Director for the Center for Hybrid Approaches in Solar Energy to Liquid Fuels, and some of you know that is CHASE. And we're really excited to be partners with UNC in CHASE. She also serves as a director of undergrad studies in the department at Chapel Hill. So she's doing a lot there. She received her bachelor's from MIT, where she worked with Dan Nocera. And then she was an NSF graduate research fellow working at Caltech with Harry Gray and Jay Winkler. And then she went on to a postdoc, which is where actually I met her, where she was an NSF ACC postdoc fellow with Daniel Gamlin at University of Washington. And then in 2012, she joined the faculty at UNC. Her research group explores charge transfer processes associated with solar fuel production, including proton-coupled electron transfer reactions and electron transfer across interfaces. Her research bridges molecular and materials chemistry and relies heavily on methods of physical or inorganic chemistry, including transient absorption spectroscopy and electrochemistry. And we're going to hear some about that through her talks. She's also talking not only today, but then there's a chemistry talk seminar tomorrow. And the time on that is 3 o'clock tomorrow in the chemistry building. So you have to cross the street. She has won the ACS Harry Gray Award for creative work in inorganic chemistry by Young Investigator. Also a Sloan Research Fellowship and a Packard Fellowship for Science and Engineering. So we're so pleased to have you here, and I'll step down and there'll be time to ask questions after the talk. So thank you.
All right, well, thank you, Karen, so much for that introduction, but also for this opportunity to be the inaugural Vagelos Institute lecturer in energy and science, engineering and science. So today, I'll wait for the slides to load. Here we go. Oh, that's right, I can fill the space. Yeah, all right, so holistically, my goal today is to introduce everyone in the audience. And I know everyone here comes from different backgrounds and kind of have had different exposures and different experiences, both to the energy challenges that our planet faces and also to chemistry. So what I hope to do today is to share with you a story about kind of my research journey and some of the problems that drive and motivate that research. So I think I'd like to just kind of start out by talking about some of the changes that our planet has been experiencing. And we can see this if we look simply at the temperature, the average mean temperature that our planet is experiencing. And if we look back and see the trends over the last 100 years, it might be an understatement to say that it's alarming. We are seeing those mean temperature changes of exceeding 1 degree Celsius and on a very, very clear trajectory. We can attribute these changes to our climate directly to human influence. And that's because this trajectory and this trend line very much mirrors what we see in CO2 concentrations in the atmosphere. So I don't have these overlapped, but I think we can see clearly that these are the same trend lines. And so CO2 concentrations in the atmosphere that are rising can be directly attributed to the burning of fossil fuels and the general industrialization of our global communities. And so we see these CO2 concentrations that are at staggering levels, higher than they've ever been before. We see these temperature rising, but we also see these secondary effects in sea levels rising, in sea ice decreasing. Just 3 weeks ago, a piece of sea ice the size of New York City fell off the eastern side of Antarctica. And that was believed to be an area that had been really protected from the effects of climate change. And whoosh, gone. All right, the glaciers are retreating. And so we ask the question is, what's going to happen to our planet, to our society, if these temperatures continue to rise on this trajectory? Well, extreme heat is going to become more frequent and more intense. We're going to see more rainfall. That's going to be coupled with flooding. We're going to see droughts in some communities. We're going to see more and more wildfires. We already are seeing more and more wildfires, and my family in California is bearing the brunt of that, having been evacuated from their homes time and time again. And we're also seeing our oceans not only warming, but as they absorb more and more of that CO2, and they are becoming more acidic, and that is destroying natural fish and coral populations and really kind of challenging our biodiversity. And so this is what's happening around the planet. But here in Philadelphia, I know you guys are all experiencing these effects too. Most notably, I think just back in the fall, when Hurricane Ida came through this region, and there was massive, massive flooding from the Schuylkill River, flooding all parts of Philadelphia. This alone is tragic. This was also accompanied by a major kind of overload in the sewage systems, flooding raw sewage into our river systems. And these sorts of events are becoming more and more frequent, not just here in Philadelphia, but around the world. And so what are we doing as a society? Well, back in November, the UN Climate Change Conference was held. This is the Conference of the Parties. This is a conference that has been held every 5 years. And so this one in November was held in Glasgow, Scotland. And the people attending this conference was primarily government representatives and negotiators, as well as big businesses and really concerned citizens. So this was a huge, huge event. And this followed the Paris Climate Conference that was held in 2015. So these meetings were typically supposed to be every 5 years. I think COVID delayed the one in Glasgow. And what happened in Paris was kind of groundbreaking in terms of what people said they were going to do. So in Paris, the countries in attendance agreed that they would work together to try to stop climate change. All right, and they were going to try to arrest these global temperature changes to stop below 2 degrees, but really they'd love to aim for 1.5 degrees. And what I showed you at the beginning, we're already exceeding 1 degree. All right, but they also want to adapt to these changes and really finance efforts to deliver on these. And so we come back and what are these numbers? Are they arbitrary numbers? We're already at 1 degree. Why are we saying 1.5? Why are we saying 2 degrees? All right. So if we exceed 1.5 degrees and just are in that 1.5 to 2 degree region, all right, what we can expect is water scarcity in many parts of the planet. All right, and that is going to have effects on agriculture, which is going to really limit access to food. That ocean warming and acidification, of course, is going to limit access to seafood. And then we're also going to see this on agriculture, livestock herds. And then people are going to be exposed to heat. But if we exceed that 2 degrees, and especially if we ever came close to 3 degrees or above, all right, that's going to be the tipping point. We're going to lose the ice sheets in Antarctica. We're going to lose our forests. We're going to see massive, massive sea level rises that we're going to completely wipe out coastal communities. All right. And again, all of our food sources are going to be threatened. So the problem with what happened in Paris is that there was this commitment to limit things, limit climate or global temperature changes to 2 degrees with a hope of 1.5 degrees. All right. But how we were going to get there and the commitments to stop the change failed to meet that 1.5 degree threshold. All right. So people pledged things, but then they didn't really enact them. All right. So those current policies fell short of what was being pledged, and that fell significantly short of what we need to do to limit change to 1.5 degrees. So coming together in Scotland, we now had the Glasgow Climate Pact. There was a lot to be said here, but I want to focus on the efforts to kind of change the energy landscape, because that's the focus here is, what can we do to move away from utilizing fossil fuels that are flooding our atmosphere with carbon dioxide, and how can we focus on changing those emissions? So there was a clear statement in this Glasgow Climate Pact to phase down coal power. People would have liked to see phase out, but that language was not used, much to some chagrin. But we see a phase down of coal power, all right, as well as a phase out of fuel subsidies that are not efficient. And that, of course, needs to be coupled to a phase in of renewables. So that's kind of what's going on. And as I spent a lot of time in November reading about what was going on in Scotland. And I think what really, struck me most was the Prime Minister of Barbados, who really spoke for small island nations who are really going to be impacted by these changes in climate most. And she really challenged the larger nations. And she poked holes in the promises that were being made by telling people these promises are being made on technologies that do not exist. And if you think about making promises like that, I think she captured it best. She said, this is at best reckless and at worst dangerous. So to me, this really clearly stated this challenge to scientists and engineers. All right. It's very clear to us that we need to rise to the occasion and advance the science and the technologies necessary to realize renewable and sustainable energy options. And I think places like the University of Pennsylvania, in particular, the Vagelos Institute, are taking the right strategy by bringing together scientists and engineers to address these challenges head on. All right. So here at Penn, we're bringing people together, or you are bringing people together to really, think about how do we advance the science and technology needed so that the things that we're making promises about are based on real technologies. So let's think about sustainable energy options. If we project out our power needs for the end of this century, that's somewhere on the order of 43 terawatts. Now, if we kind of think about different sustainable energy options, there's a whole slew of things we can consider. Wind power, hydroelectric, geothermal, biomass, solar are among our sustainable energy options. Now, I will be the first to admit that I don't think any one of these single energy options will be, the panacea that will solve everything. All right, but we're going to need to leverage these sustainable energy options together to change our global energy portfolio. But to me, I think the real potential is in solar energy, because such a tremendous amount of energy is accessible from the sun. And so what are the obstacles to solar energy technologies? If I had been giving this talk 10 years ago, I could have told you that, well, solar photovoltaics exist, but the real issue is their cost. They're just not economically competitive with fossil fuels. And so unless we incredibly subsidize them, we just can't make an impact on the energy market. It turns out that the costs have come down tremendously on solar photovoltaics to make them very cost effective. Why? Well, scientists and engineers figured out how to make these better, more efficient, and brought the cost down. So that's a huge win for science and engineering. But there's still obstacles to integrating solar energy into our global energy portfolio. And that has to do with how we as a society use energy. So if we look at our energy usage, which is shown in these blue bars right here, we see there's a high demand in the morning and a high demand in the evening. So I, like many of you, may come home, perhaps want to turn my lights on at night when it gets dark out, maybe watch some trashy TV, maybe do my laundry. So I'm putting a huge load on the power grid in those evening hours. But that's not commensurate with when we are harvesting solar photons. That's peaking midday. All right. And solar photovoltaics capture the solar energy, the solar photons, convert that to electricity for use on demand, but they don't store that energy. And so the big challenge here is energy storage with solar. So how can we think about storing solar energy? Well, there are a number of different strategies. We can imagine taking that electricity from the solar photovoltaics and using that energy, electricity, to pump water uphill during the day. And then we could release it at night to drive turbines. So that's one strategy. Battery technology is one area I think that has shown tremendous scientific advances, again, in the last decade. And we're seeing the marketplace explode with plug-in hybrids and electric vehicles, grid scale batteries. You can get that Tesla home network to have your own energy backup batteries in your house. So that's a clear opportunity here for us to store energy. But one area that is really attractive to me is the idea of storing the energy of solar photons in chemical bonds, in a chemical fuel. And the reason for this is because this is exactly what green plants are doing in the process of photosynthesis. So green plants are going to capture light and take water and carbon dioxide and produce oxygen and sugars or carbohydrates. So this process has been well worked out. And the carbohydrates right here are the plant's chemical fuel. Now, I will be the first to admit that I am not an organic chemist. And to me, the idea of synthesizing carbohydrates sounds very daunting. In fact, when we interview people that teach organic chemistry at UNC, we make them give a lecture on carbohydrate chemistry, because that's like the most challenging thing to teach. But we don't have to target such complex chemical fuels as carbohydrates. We can look towards simpler things. We can split water into oxygen and hydrogen itself is a fuel. We can also couple that to the carbon dioxide reduction, which I'll show you shortly. But this is a very simple, I think, infographic that shows you if we could create a solar fuel production system, which may or may not look like these cute little leaves. All right, we would capture the solar photons and then use that energy to drive the splitting of water into hydrogen and oxygen. And so if you were in general chemistry and you opened your textbook, you would see a picture like this. that looks at the kind of general thermodynamics of this reaction. So if we take water and we want to split it into hydrogen and oxygen, we need to put energy in. And that energy input could come in the form of photons. And then we have our hydrogen fuel and our oxygen. And if we combine those either in a fuel cell or a combustion engine, this is the BMW right here, hydrogen combustion engine car. We combine them and we release energy and reform water. All right, so this is a very basic concept that we can adapt from nature, but how might this integrate into our general life? Well, we can imagine having large area solar fuel production systems that are coupled to hydrogen storage. All right, and then we can use that tank and feed that into a fuel cell for electricity generation for large buildings, or directly into a hydrogen fueling station. And this will look even more attractive if I coupled this to CO2 reduction and was simply making a liquid fuel. So we can imagine doing that kind of on the left-hand slide here. Here's a picture that shows how we can use solar energy to drive the splitting or drive the conversion of carbon dioxide and water into carbon-based liquid fuels. And that's super attractive because now, first of all, we are storing our fuel as a liquid. That has energy transportation advantages there. But it also allows us to feed those carbon-based products into existing technologies that can take those to fertilizers or plastics or pharmaceuticals or other sort of synthetic fuels, for instance, for airline travel. And and perhaps replace a lot of the materials that we now get as byproducts in the petroleum processing. All right, so where do our technologies stand here? So I said we want to start with solar energy and we want to end up with storage, ideally in the form of liquid fuels. All right, so there are technologies that exist to take solar energy to electricity. That's what we've been talking about so far. We can take that electricity and we can electrolyze water to make hydrogen. That's a technology that exists now. And then there's some synthetic strategies that allow you to take hydrogen and CO2 to create liquid fuel. So this is be a three-step process if we let everything operate individually. But there are strategies that allow us to envision using solar energy directly to drive the splitting of water, which I've already talked about for solar hydrogen production. There's also strategies that allow us to take electricity and drive the production of chemicals, carbon-based chemicals in electrocatalytic processes. But really, this is the holy grail of being able to take solar energy, water, and carbon dioxide to drive the production of these targeted liquid fuels. And that is truly artificial photosynthesis. And so, as Karen mentioned, my research is part of the CHASE family, or the Center for Hybrid Approaches in Solar Energy to Liquid Fuel. And CHASE has a mission to really advance the key fundamental science that is necessary to create technologies for artificial photosynthesis. And our scientific strategies focus on the concept of hybrid photoelectrodes, which I will introduce on the next slide, that allow us to create storable solar fuels from water, CO2, and sunlight. CHASE is a research center that spans 6 institutions. We are based at UNC with 5 partners: Brookhaven, North Carolina State, Emory, Penn, and Yale. And I want to highlight, for those of you who are less familiar with CHASE, the key researchers in this room, on Zoom, or on your campus here, who are critical players in advancing CHASE research. And I hope I've captured everyone, and I apologize if I missed a name here. But these are all key players in helping us work as a team to advance solar fuel technologies. So our research goal centers around this concept of hybrid photoelectrodes. Now, hybrid photoelectrodes are based on molecular catalysts that are capable of mediating the bond rearrangements and the movement of protons and electrons that allow us to synthesize chemical fuels from CO2, water, or potentially nitrogen as a feedstock there. These molecular fuels would be integrated with semiconductors that are able to capture those solar photons and separate charge. And we recognize that when we integrate these molecular catalysts on the semiconductor light absorbers, we will place those catalysts into a unique microenvironment. And we can tune that microenvironment or exploit that microenvironment perhaps to control what products are being generated, and hopefully also address issues related to durability of these systems. And then finally, what we hope to do is to exploit multiple catalysts that work together as a team to generate high-value liquid fuels in what's called cascade processes. So just like Chase is working as a team with all of our researchers, these catalysts will partner up and work as a team, pass off their reaction intermediates one to another to access those high-value liquid fuels. So why might we take a strategy like this one? Why are we relying on molecular catalysts to carry out the fuel-producing reactions? Well, molecular catalysts are highly attractive to us because they are known for their high selectivity, including some of which can go all the way to methanol as a liquid fuel, one carbon-based liquid fuel. But beyond knowing that they have this high selectivity, they are highly tunable. And we can build relationships between properties of those molecules with their activity. And that allows us to really have clear design principles that allow us to advance these catalysts. And so we can improve them to address issues like their activity, how fast they are, all right, how stable they are, that's durability, what products they're making, that's selectivity, and really how energy efficient they are, and that's over potential. And then finally, what I think is kind of makes them a fun playground is that we can really elucidate how these mechanisms, how these catalysts are operating using tools like electrochemistry and spectroscopy, and really paint a picture of what's called their reaction mechanisms. And so I show you here exactly the tunability of molecular catalysts in terms of CO2 reduction. So if we start with a basic molecule, and I've abbreviated that here as this LM species, that species can react with CO2, all right, and then react with protons and electrons to funnel towards products like carbon monoxide. We can intercept one of those intermediates, the metal CO species, and react that further to funnel towards a reaction product that would give us access to methanol. But if that initial species doesn't quickly bind CO, but instead reacts with water or proton sources in solution, we can totally transform the reactivity and drive instead towards carbon monoxide as a product or methanol as a product, formic acid, or access hydrogen. And in this case, if we're targeting liquid fuels, maybe hydrogen isn't our reaction of choice, but understanding the mechanisms that get us the hydrogen allows us to redirect towards the more productive fuel producing pathways. And so molecular catalysts really enable us to access a huge reaction space, redirect reactivity down the right pathways. Now, semiconductors really are where we're going to leverage solar photon capture. And we can leverage advances from the semiconductor industry over the last many decades to our advantage and take advantage of science that exists to integrate our molecular catalysts with these light absorbers. And then there's tremendous power in tools like spectroscopy and microscopy that allows us to examine these new integrated materials. And we expect that we'll be able to study these extensively, again, to understand issues associated with how durable or how selective our resulting hybrid photoelectrodes are. Now, once we bring the catalyst and the semiconductor together, we bring that catalyst into a new microenvironment at the electrode surface. And this is an exciting opportunity for us to create new control over what's going to happen. We can exploit that microenvironment perhaps to redirect the reaction pathway one way or another. And we might be able to use that microenvironment to enhance the overall durability of our molecules. We expect that this will be challenging to interrogate, but with our world-class microscopists and spectroscopists, we expect to be able to gain insight into the molecular structure of these species on the surface. And interpreting that, of course, will rely a lot on our theoretical and computational chemists. Now, finally, I alluded in my introduction slides to Chase about this idea of teamwork between catalysts. So far, I've shown you that we can access, in some cases, methanol as a product, but in many cases, we access carbon monoxide or formic acid, which are other carbon-based products that have one carbon atom in them. Methanol has high energy density, but the other species are just been reduced. CO2 has been reduced by just 2 electrons, which lowers their electron or lowers their density. And of course, CO is a gas. So you could call me out on that and say, hey, you were looking for liquid fuels. But it turns out that the idea of taking those initial products on further is an opportunity for cascade catalysis. So we could have a first catalyst that takes CO2 to CO or formic acid, and then the second catalyst that intercepts that intermediate and takes it on to our energy dense liquid fuel, some sort of alcohol. This is a place to leverage advances in organometallic chemistry, which is well known for enabling carbon-carbon bond formation. So we can imagine getting things like ethanol or butanol or things down the line that are really going to plop into our existing energy technologies and allow us to kind of see a place for liquid fuels in our society. Now, of course, doing this and this whole idea of like handing one intermediate off to the other, like reminds me of like being here at Penn, because this is where the Penn relays are every year. So you gotta like bring our, I was like a track star, not a track star, a track participant, far from a star in high school. And I always dreamed of going to the Penn relays, right? So we got hand off one intermediate to your next team player. And that's exactly what's gonna happen here. All right, but we gotta make sure that we understand how fast the first relay leg is running and how fast number 2 is gonna be running, all right, to really enable clear handoff of those intermediates. So there's a lot of science challenges here. So I laid out kind of the strategy and some of the challenges here, all right? So I wanna finish my talk by telling you about some of the science that we've done in Chase so far. And I'll focus on what's going on in my lab and leave a chance for all of the audience here to have a reason to talk to the Chase graduate students and postdocs here to find out what's exactly going on there. So I'm not going to steal their thunder, but I'll give you a little bit of a taste of what's going on and some of the work we've been doing. So let's talk about this whole idea. I made it sound very simple, like we were going to take these molecular catalysts and just put them on the semiconductor. We may have thought that was going to be simple too, all right? It turns out that just doing that can be very challenging. So we've got our catalyst, but now we need to figure out how to like put something on the back of it that allows it to stick to the semiconductor. So we got to do some modifications there. And then we might have to modify that semiconductor so it's ready to like grab that anchor and react with that. All right. We're also going to have to make sure that all the chemistry there that we're doing is compatible with those molecules and not going to destroy them. And I say this because we've done a bunch of chemistry to try to attach the catalyst to the surface, not destroy the catalyst. And then finally, we need to convince ourselves that those molecules, once we do this reaction to put them on the surface, they are still molecules, all right? We need to convince ourselves, and that's going to require a lot of spectroscopy, a lot of microscopy, and theory to kind of interpret those data. And so I'll show you some exciting results that my graduate students, Brittany Huffman and Gabriela Pereira Ferron, have done together with our collaborators at NC State, Hala Atala, Phil Castellano, and working also closely with Carrie Donnelly, who is one of Chase's staff scientists. So they've grabbed this rhenium complex that Hala has prepared. And this is a complex that is capable of reducing carbon dioxide to carbon monoxide. So this will be one of those first steps in the cascade. Hala was able to append a kind of backbone on here, a carbon-carbon double bond or vinyl group that would allow us to exploit a hydrosilylation attachment strategy. And Brittany and Gabby were able to take their silicon substrates and work with under some really daunting and corrosive, terrifying conditions, working with what's called hydrofluoric acid to etch off the surface and create a very pristine environment that terminates the silicon with hydrogen. And they have been able to show and exploit some acoustic cavitation methods to attach this catalyst to the silicon surface. So now we're taking the catalyst that does the chemistry with the silicon semiconductor that absorbs the solar photons to create this integrated hybrid photoelectrode. They've gone ahead and known that attaching this complex right here doesn't cover the whole surface. And now we might have some fear of some durability issues with the resulting silicon substrate. So they've reacted the rest of the sites with these long alkyl chains to prevent additional what we call oxide growth that would hinder this new surface here. And then they've been able to use some surface-based spectroscopy advanced within Chase to ensure that this molecule that we put on the surface is still the molecule. And so all of what I've highlighted in red here are those COs that are attached to the rhenium center. They have vibrations that are very diagnostic of being attached to that molecule and affirmatively show us that there is still this molecule on the surface. And then some very exciting recent work, we have been able to see that we can drive this catalysis with light and see responses that are consistent with carbon dioxide being reduced to CO with solar photons. So last week, we had all of our product detection equipment installed in Chase headquarters at UNC. So that is now online and operating, and maybe today while I am here, that product detection is now finally able to happen. So we've been able to put molecules on the surface and start driving at least that first stage in these cascade catalysis with solar photons. So that's an exciting win. And we're not the only ones in Chase who have been able to show this. All right. There are lots of examples of finally overcoming those huge challenges of getting the molecules on the surface and being able to drive that production with light, or contributing efforts to make that possible. So now let's talk about this idea of the microenvironment. So I told you earlier that we can bring the molecule to the surface and attach it to the surface, and now it's gonna be in a new neighborhood. We might also be able to give it some new neighbors. All right, so this P right here, we could park a P right next to our catalyst, or maybe we'll attach P to the catalyst. And P is going to be some sort of reactive group. It could be something that's charged. It could be something that's acidic. All right, something that's going to influence the microenvironment. I'm not going to talk right now about adding friends to the neighborhood here in the microenvironment, but I'll talk about what just the new place this catalyst is in and what it's experiencing. And I'll call this the native microenvironment. So when the catalyst hits on the surface, it's going to be influenced by an electric field at the electrode. It may experience a local pH at the electrode surface that's different than the bulk solution, and that's going to impact the availability of the protons that it does this chemistry with. We're going to have experiences like the electrolyte, the solvent dielectric will all influence what's going on here. But what I'll tell you about in my last couple minutes here has to do with the linker properties and the surface properties. And so for this, what I'd like to share with you is a brief story, not about a catalyst, but about a small redox active reporter molecule that can inform us a lot about what's happening in that microenvironment. And so I'll briefly tell you about 3 different surface materials. Silicon's over on the right. That's our semiconductor light absorber. But we've also been able to integrate this with a dark electrode, so an electrode that doesn't absorb light. But if we attach it to a potentiostat, we can push out electrons. And I'll tell you about 2 carbon materials, amorphous carbon and glassy carbon. And as I've listed these from left to right, we can see clear changes in order. And just before coming over here, I had the chance to spend about an hour over in the Sync Center, and I can affirmatively tell you that all of the tools in that building could help support to this argument and have supported the argument that amorphous carbon is a highly disordered material, silicon is a highly ordered material. So we can probe, that with microscopy and spectroscopy imaging. But what I want to show you is that when I put a redox active molecule or a catalyst surrogate on the surface, what's happening in that redox chemistry is actually informing me about that unique microenvironment as well. And that's really powerful to imagine being able to use electron transfer processes to inform us about that local microenvironment. So it turns out all of these materials are able to undergo a reaction that terminates the surfaces with chlorine atoms. We can react that with a ferrocene molecule. This is that iron complex right here, the Fe, with the kind of rings around it. So ferrocene we put a long tail on it. We could do some chemistry called Grignard reactions. Turns out this is one of these relatively harsh processes that not all catalysts can stand up to the harsh Grignard reaction conditions, but ferrocene is tough and it can. So we can put ferrocene on all of these surfaces using the same reaction. So I want to tell you about amorphous carbon because this is the most disordered material, which means it's the most interesting. All right, so in my lab, Debanjan Dar works with Catherine McKennis, who is a graduate student in Matthew Lockett's group at UNC. And they work together to fabricate these amorphous carbon materials by sputter coating the amorphous carbon onto FTO-coated glass. Now, FTO-coated glass, it turns out, is an intrinsically rough material. And so that imparts some kind of physical heterogeneity. And I'll just do this and tell you it's bumpy. All right, that's how you should think about it. But it turns out that if you're an organic chemist and you kind of peer into this carbon network, you're going to see a whole mess of 5, 6, 7, and 8-membered rings, which also is going to tell you that there's a mix of sp2 and sp3 carbons. All right, and that's going to create different reactive sites that can undergo this reaction to form the attachment to the ferrocene molecule. So already we have this spatial and chemical heterogeneity in our material. And when we put the ferrocene onto the surface, it turns out that we get a disordered monolayer of ferrocene. Now, in learning about order and disorder in the literature, it turns out that the word random means ordered. And that blows my mind, but so I'm not going to use that terminology here. So disordered means that they're kind of scattered. They're not all lined up like formation, like soldiers in formation here. They're all kind of scattered around here. All right. And each of those ferrocenes can feel its neighbor through a process called lateral interactions. So when I take an electron away from ferrocene or give it one, and we do the same thing to its neighbors, we see this sort of charge repulsion. That repulsion between the individual ferrocenes is basically a way that that ferrocene knows it has a neighbor. So we call those lateral interactions. And those lateral interactions create non-ideal factors in our electrochemistry that we can see in our measurements. And so this disorder plus the lateral interactions is really imperative in allowing us to have a readout of the disorder. So I've highlighted this one ferrocene. The blue dots are supposed to be the different ferrocenes. I've highlighted one in red. And basically what you can see is that in a perfectly ordered surface, it would have one ferrocene on the left and one on the right. They'd be equal distances apart. But in this disordered system, it doesn't have neighbors equally spaced out. And those sort of unbalanced reactions coupled with the lateral interaction processes create information that we can read out in our voltammetry experiments that allow us to affirm that we have this disorder in this material. And that disorder is created by the local microenvironments. Now, if we play around with these ferrocene molecules, which I've abbreviated FC here, I can kind of change how long their tails are, all right? And that allows it to kind of access and move around and avoid its friends and doesn't want to feel that lateral interaction. So the longer the chains, the more flexibility it has to avoid those lateral interactions, and the shorter chains, it's in trouble and it can't. And so we can kind of use all that flexibility, again, to support these arguments that the lateral interactions are arising from all of this spatial and chemical heterogeneity. So that is the most interesting material. I'll tell you a little bit about silicon and carbon. In carbon, in work that Brittany has led, we see the same sort of lateral interactions when we oxidize ferrocene. All right, we saw some really interesting responses where the peak broadness wasn't what we would have expected in terms of the amount of lateral interactions. And ultimately, we're able to model and find out that as we modified these surfaces, the ferrocene was choosing to hang out with other ferrocenes. They were like hanging out in the clump in the corner, and there were fewer ferrocenes that were isolated and hanging out. And as you change the surface coverage, you could change the relative populations of the isolated ferrocenes and the clustered ferrocenes. And so each of these ferrocenes, kind of subpopulations, experiences a different microenvironment too. The isolated ones are a lot more exposed to the solvent. The clustered ferrocenes have a different kind of local microenvironment. And then finally, if we end with silicon, this is work that Brittany and Gabby did together with a whole bunch of folks, some of which here are at Penn. And they've been trying to explore ferrocene on silicon. And the long story short is that silicon is a very highly ordered material, and everything is much more well-behaved. So we've been able to get really robust electrochemistry measurements. There still, of course, are those repulsive lateral interactions, but they're much more balanced across the surface. We have much more order, and we've been able to really use some exciting chemistry to show that there are molecules on the surface here, including things like ellipsometry and X-ray photoelectron spectroscopy. So again, proving to ourselves that we have molecules on the surface. So with that, this handy watch I'm wearing allows me to tell me that it's time to stop talking and let you guys answer all the questions. So I hope I've been telling you a little bit about how scientists are rising to the challenge of advancing energy technologies, in particular, energy technologies that are going to enable the production of solar fuels. So Chase has a strategy, and I hope if I ever got to meet Mia Motley here, right here, she would embrace what we as scientists and engineers are doing to drive the production of solar fuels and critically advance this technology that turns this from a concept into a realized technology that can address the major issues of global climate change. So none of this, of course, would have been possible without the people involved. I'll start first with the researchers in my own lab. I tried to highlight the folks whose science I was able to highlight today. I know I talked just about a tiny fraction of all the work that's being done. So they're a tremendous group to work with, and I'm so grateful every day to have them as part of my team. I'd of course like to thank the people who funded the research and give you the most official funding information. So the work I talked about today on silicon was all funded by Chase from the Department of Energy, and the work on carbon was funded by the Department of Energy through a separate award. And the opportunity to solve this global scale challenge requires a global scale team. And so I've been so grateful to be able to be part of Chase and work together with scientists all across our country, mostly on the East Coast, or all on the East Coast. And they've been an incredible team that's really pushed me outside my scientific comfort zone, allowed me to flail, learn new things, and I'm excited to be uncomfortable and help advance the science. So with that, I want to thank everybody who made the trek out to here, who logged in on Zoom. And I'd be happy to join Karen on stage and answer any of your questions. So thank you.
Well, that was terrific. Thank you so much. And we are now going to, the one thing I forgot in the introduction was to actually thank the Kleinman Center for hosting us here in their forum. We're very grateful. And in true Kleinman Center mode now, we're going to step up here and sit in these chairs, not something scientists typically do in this way.
I kind of
So
want to sit down after a talk. This is nice.
feel like I'm on a nighttime hosting thing. So we'll open it up to questions from the audience, and questions on Zoom are being handled up here by Eric in the second row. So thank you, Eric. So any questions to get us started here? We have a question from the back.
Microphone, so you hear me. Oh, first of all, fantastic talk. I really enjoyed that very much. Nice to see the whole perspective of what you're doing. I have a sort of a high level question about the concept of solar fuels. It's one of scalability, because, you know, for traditional chemical processing on surfaces, you use very high surface area materials. Here, your solar collector is inherently low surface area. And for like solar cells, we just put in big mass arrays of them. You can do that. In theory, you could do the same thing here. But then you're going to be producing, it's easy to collect electrons. It's harder to collect gaseous products.
Yep.
You're going to have a low pressure of a low concentration spread out over a long area. So how does that fit in? Have people, that's beyond the science that you're doing, of course, but
Yeah,
is scalability here an issue that people worry about?
absolutely. And, you know, I think you allowed me to deflect the responsibility for addressing scalability to others, so thank you. But, you know, I see this obviously as a partnership between scientists and engineers. So what we're focusing on right now is the fundamental science challenges that are impeding technology development. I do think that there are a lot of technical challenges that if the science is working, the engineers will make work. So I'm placing a lot of faith in them. But to answer your question more specifically, what are some of the strategies and approaches that we can leverage? So we can texture our silicon naturally to create higher surface area. That may be attractive for some characterization methods right now, but in other cases, when we're trying to detect the molecules on the surface, we want the surface to be nice and flat so we can kind of pull out the molecular properties on top of that. So that's one advantage of just starting with kind of the planar materials. But if we texture them or nanostructure them, you can increase those surface areas, you know, probably by over an order of magnitude. So that's a simple kind of science engineering strategy. Collecting the products, especially, you know, if we're working in water and now we're generating methanol, ethanol, butanol, how do you separate out that product? There's obviously, you know, distilleries, right, that figure this out in some of the industry already. There's likely going to have to be some sort of flow process to bring the water that and the carbon dioxide saturated water across these. Maybe it's water vapor that we're working with, pull, and then allowing liquid fuels to drop out. These are kind of off the cuff responses, and I'm sure Karen may have better ideas here. Other people in the audience, I welcome them to weigh in too as part of this discussion. But of course, you're right that there is going to be scale issues of how do we do this. I look forward to seeing those solutions. Do you want to add anything?
No, I mean, I think a lot of this is still the very basic science phase, and we're behind where we should be. We should have been starting on this a long time ago, but we have to get there. And I think the scaling will come. We have to get the basic science down to be able to do these transitions. Other questions?
Great talk, thank you. So I had a specific question about the cascade catalyst strategy. When you introduced it, you mentioned passing off intermediates, and I think you use CO as a great example of an intermediate that could be envisioned. But when you think about the passing off, are you envisioning using the lateral interactions between species to directly transfer these molecules, or are you envisioning like a gaseous molecule that's in solution, like buildup of an intermediate versus direct transfer?
That's a great question. Now you're opening the idea of this direct transfer to me, which is intriguing. Most likely we would be relying on mass transport. So building up the intermediate, relying on diffusion of that away from catalyst 1 to catalyst 2. On the fundamental science level, that opens up tremendous opportunity to understand the reaction kinetics at the individual catalyst sites. Because if you know how fast we're building up the product, and then how fast catalyst 2 consumes that product to make, take the intermediate to the product, that tells you the ratio of catalyst 1 to catalyst 2. It tells you how far apart you need to space them on, some sort of pattern structure. Maybe what that patterning looks like, because you can combine that with mass transport properties based on what exact environment you're in. And all of that, I think, is a really exciting opportunity to combine measurements of kinetics with microkinetic modeling that would play into exactly how we would pattern these catalysts together. So Karen Goldberg is the lead of our Cascade Thrust in Chase. So she thinks a lot about bringing the catalyst developers, the kinetics measurers, the surface patterning people, and the microkinetics modeling together to make that happen. So
Yeah, I mean, I think the key in all of that is that you have to think that this is really how nature works, right? So when nature converts one molecule to something else, it does it to a path that involves the production of many different molecules. And there are enzymes that take molecule A to molecule B. And then another enzyme steps in and takes molecule B to molecule C. And that's how we build up from something like CO2 to sugars, right? It's a stepwise process that involves many catalysts along the way. And that's essentially what we're trying to do, right? And that's what all these, designing the microenvironment around each of the catalysts has to do with, when you think about a biological system, there's a whole sphere of other stuff around each of those, in each of those enzyme pockets, right?
Thank you for a wonderful talk, both the general introduction and then the sort of a somewhat deeper dive into the science. I know tomorrow will be even deeper. I have a question regarding efficiency, and I hate to use the word because it obscures a lot of the important basic science. But if we think just about the microscopic perspective that you're taking on the problem, what is the current quote unquote efficiency relative to where you would like to be? And what perhaps will give you the biggest bang for the buck in terms of getting there?
that's a great question. So I'll answer two things. So if we compare this to nature, nature is incredibly inefficient with about 1% efficiency. And so that sets the bar pretty low in some ways. We could be champions if we could break down nature. But of course, efficiency is going to dictate scalability, right? And the higher our efficiencies, the less land mass we need to use, and the less raw materials we need to use. And so efficiency is going to be an important metric that we would consider as we advance these solar energy strategies. What we're working on right now is focused on, again, realizing the fundamental science to access these. And one of the really attractive approaches about our hybrid photoelectrodes that we're building is that they leverage a true molecular level understanding of the molecules, that semiconductor surface, and that microenvironment. And all of those can be tuned explicitly through modifications on the atomistic level. And those allow us to create relationships where we might be able to correlate kinetics or how fast something is happening with some sort of property, and that's going to translate directly to efficiency. So I really because we're again, in the fundamental science, I don't have an efficiency number to throw out at you, but I believe our strategy is going to lend itself towards having a clear pathway towards whittling down and improving the efficiency with the strategy we're taking. So.
Oh, that really was a great talk. Thank you. In your early slides, you showed, I want to get back to charge separation, and you implied that, there was a reduction and there's also an oxidation subsequently. And in terms of your cascade catalysts, I mean, how much charge separation are you going to rely on? How close do these two different steps have to be? If one of them is using the electron, the other is using the hole, I mean, you only have one side of a flat piece of silicon. You're not making an actual.
Yeah, you are highlighting a lack of clarity in what I presented today. Yeah. So no, that's an excellent question. So what I think I failed to highlight in my presentation was the ultimate approach, which would rely on an oxidative side and a reductive side. So we would separate that charge and across either a tandem cell that has two light absorbers, maybe one's a photoelectrode, one's a dark electrode. But we would take the electrons to carry out the reduction processes. And on the other side of the cell, we would do exactly what nature is doing, which is oxidize water to O2. And then pull that, what that allows us to do is to pull the protons and the electrons out of water directly to feed into the reductive sides. Now, in terms of these cascade strategies, we envision them all being reductive strategies or carbon-carbon bond formation, so like stitching together things. So, but thank you, that was a lack of clarity on my part. So.
In terms of the generation of fuel and an organic molecule, you started out by talking about, I guess, reducing proton and then protonating that to form hydrogen, and then going on to capture of carbon. Do you have an intuition? And the other example that you gave was going to sugar, right? Do you have an intuition of what your optimal organic molecule is as the fuel?
Oh. How
How complex do you want to go, and how much energy do you want to build into the molecule?
That's an excellent question. So yeah, I started out by knocking my ability to make carbohydrates. And I think, of course, carbohydrates, nature has evolved to create carbohydrates because they're building blocks for nature to create cellulosic walls and, create the structure of the plant. And for us, we're not trying to build a plant with these chemical building blocks. So that's one reason that carbohydrates aren't our strategy. So we think about what is our energy kind of economy based on? It's coal, natural gas, and liquid fuels. Liquid fuels are incredibly attractive, again, for the transportation sector, or just transport from where we create the solar fuels to where we use them, which is a lot easier than the gaseous fuel. So I think ultimately a liquid fuel is the ultimate goal. Which liquid fuel is another question to be answered. So the more carbons in that liquid fuel, typically, the more energy dense that fuel is going to be. And so balancing that in terms of the accessible chemistry is going to be one driving factor of that. And then probably the efficiencies of all the steps versus the density that you get out will be another driving factor. So I think there's going to be some interesting kind of energy economics that come into play in terms of what our strategy is going to be. And right now, advancing the fundamental science, we're going to find out what those options for the fuels are so we can kind of maybe do that math. So I don't know, Karen, would you like to add anything?
Yeah, I mean, it's certainly going to be simpler than carbohydrates. Methanol, for example, is a wonderful chemical to think about because you can transport it as a liquid. we already have the technology to take that on to liquid fuels. So that already exists when we talk about technology that exists or not. If we can make ethanol, you've all seen that ethanol is added to your gasoline. Well, if you can take ethanol and convert it to butanol, that's even better because you can add it in much higher amounts to your gas. And I see Don shaking his head there, but you can add it in higher amounts to your gasoline. I know that. Well, that may be, but we need to transition. And if you just target technologies that are going to be all the way to zero carbon and not help us in the transition, I think that's in danger, right? Because I think that we're going to be at that 3 to 5 degrees before we figure all of that out. So I think we need to transition, and that's going to be on the path to transition, right? So if we can at least take the CO2 out that we're going to use and then turn it back into CO2, you're creating somewhat of an anthropogenic carbon cycle. So something like butanol then is going to have a higher fuel value. You can mix it in higher proportions than you can currently put ethanol in your car. You can put butanol in greater fraction and use that as a fuel. So I think the simpler carbon fuels are what we're aiming for, Jeff. But making the carbon-carbon bonds is really hard from CO2.
Great talk. I think on a basic level, my question is about your rhenium catalyst that you mentioned and whether or not that, I mean, to me, it looked like a light absorber, but on a more fundamental level, are you considering also using these molecules and the catalyst as tandem light absorbers? Are there opportunities there? Or would that actually just make the system messier?
That's an excellent question. So the rhenium complexes I showed, of course, have a metal center and a pi accepting ligand, which gives them a great metal to ligand charge transfer band. This specific class of catalyst has been shown to be able to operate under a molecular light absorption fuel production process. So competitive light absorption in terms of how that interfaces with the reaction mechanism will be, of course, important. Whether it does or does not will be something that we need to know. Are we turning something on when we shine light on this? In terms of interfacing it as a direct strategy, that's another opportunity, again, to increase your solar harvesting and driving, light absorption and fuel production in the same molecules. I have another arm in my research lab that is really interested in how do you right now we've got the semiconductor doing the light harvesting. Semiconductors are really good at absorbing light, and they do so really efficiently. They can separate that charge and allow us to let the molecules do the fuel production. This idea of putting those two jobs onto one molecule would be really cool. And we have some other work in my lab that is kind of tackling that same idea. Can we get molecules that can capture the solar photons, end up in an electronic excited state? And in that electronic excited state, is there something unique about that electronic structure that allows us to do the proton and electron transfer reactivity that produce fuels? Asking a molecule to absorb light and do PCET, proton coupled electron transfer, is definitely a tall order for that catalyst. So I think that's a challenge that's exciting, but that doesn't undermine these other strategies to say, can we optimize these two components to work together? And in some ways, as we think about what can we do fastest, having one molecule, the semiconductor do its job and absorb the photons, and the catalyst do its job and do the fuel production, is a good team effort.
So there's no questions on Zoom. Okay, so you've all been a great audience, and great participation. There's a reception downstairs for everybody where I'm sure Jillian would be happy to answer more questions. I want to thank you all for coming. I want to thank Jillian for a spectacular seminar. I want to thank the Climate staff, and we're so grateful for you hosting us and for joining forces in Energy Week. We're really happy to take part in this and be part of it. With that, let's thank Jillian one more time. And invite you all to the reception downstairs. Thanks.